Alkynes. They're like alkenes. So we've just had some videos where we've looked at alkenes as nucleophiles, the pi bond in particular as the nucleophilic part that goes out and grabs different electrophiles like HBr, Br2, acid, and even borane. Okay? So the same kind of thinking is applying to these pi bonds in alkynes. Most of the time we'll just be doing these reactions twice to get to our product. So, for instance, adding HBr, right? So if I add HBr to this, again, I'll picture my pi bond swinging open like that. And I get some positive charge like this, which is probably going to be trapped by that bromide intermediate. So that's great, but I still have an alkene here. So sometimes I can react it with another molecule of HBr in a very similar way to get this geminal dibromide. So geminal, again, remember twins on the same carbon, right? So again, some of this depends on the specific molecule. Sometimes elimination will be fast enough that it will want to sit here. But for an alkene like this at the end of a chain, we'll very often see a dibromide as a product. Again, just think about this as the same reaction we talked about up here, but twice. So first the pi bond gives this weird sp cation, I guess. And then from here, if this goes out and grabs a proton, now I've got some cation that looks like this, which technically the lone pairs on this bromine can actually stabilize that cation a little bit. So the selectivity of this is going to be very good. So an alkene with two equivalents of HBr can give me this geminal dibromide with both bromines on the same carbon. In the same way, alkynes will react with dibromine much like alkenes do. So here I have my pi bond going out, grabbing a bromine, making some strained cationic three-membered ring that's then opened up by the nucleophile to give me a trans dibromine, just like this gives me a bromine. There's no cis and trans here because there's no double bond. This now, since it still has a pi bond, can react with another molecule of Br2 to give me a tetra-substituted compound. So much like our last example, this is simply a case of both pi bonds reacting, so one after another. So the reaction that we would do with an alkene, we do it here twice. Once, twice. When we react these alkynes with aqueous acid, it's very much like when we reacted our alkenes with aqueous acid. We're going to end up with our pi bond as a nucleophile, grabbing a proton from the acid, getting this cation, trapping with water, somehow losing that acidic proton to water or anything else, and then ending up with an OH like this, right? You can see the similarities between these two things. This, however, is different. Because of this double bond, we call it an enol. This enol undergoes very fast tautomerization to give a ketone. So this is technically an equilibrium, but the equilibrium lies very, very far to the ketone side. Sometimes this particular tautomerism is called a keto-enol isomerization for obvious reasons. Okay, so this is a way for us to go directly from an alkyne to a ketone in aqueous acids. Your book will describe another way that uses aqueous mercury salts to do the same thing. That is a gentler reaction, but organic chemists try not to use very, very toxic reagents like mercury when we can avoid it. Actually, in modern chemistry, we really wouldn't use aqueous acid either. We would probably find some third reaction. But the important thing here is the mechanism. The idea that I can get to this from that. that if you simply look at the atoms, a ketone is simply an alkyne plus water. That's a pretty important concept, I think. So again, just like I'm able to make my alkene into an alcohol, I can make my alkyne into an enol, which will very quickly go to a ketone. Finally, when I've got an alkene and I do hydroboration on it, I could use BH3, but many times I'm going to use something called 9-BBN. Why is that? So this is 9-BBN, and the reason we know it is because it is bulky. It's a bulky borane. And it turns out that the selectivity, the reason that, if I wanted to react only on the end and not in the middle, I mentioned that it had to do with forming a cation and the selectivity there. But actually, sterics plays a pretty decent role in that too. And so the bulkier the borane is, the more selective it's going to be for that end carbon, no matter what the steric bulk of this is. So if you see 9-BBN, again, it's just a nice crystalline and bulky form of BH3. Hey, my video cut off. Let's try this PowerPoint style. So I've got an alkyne. It's going to react with this borane here. The borane could be this big bulky thing, or it could just be BH3. Boron always adds to the less crowded end of that pi bond, and after oxidation gives me this alcohol, which is, again, an enol, alkene, alcohol right there, which is in equilibrium just as before with this carbonyl compound. Only this time we get an aldehyde, whereas last time we got a ketone from the more substituted OH. So this gives us some really useful regioselectivity. I can get two different carbonyl compounds by reaction of this alkyne. So to summarize, these are the reactions that we learned. If I add HBr to these pi bonds, it's just like HBr reacts with alkenes. One equivalent will give us a bromoalkene. Two equivalents will get two additions. The bromines will add to the same carbon because bromine stabilizes the positive charge in the intermediate. If we react with dibromine, we end up with 2 and then 4 bromines on the product. If we react with aqueous acid, we get a carbonyl compound on the more substituted end. If we react with hydroboration and oxidation, we end up with an aldehyde, or at the very least an oxygen on the less substituted end. So alkynes are really versatile reagents. I can get to a lot of things from them. In the next video, we'll talk about if we deprotonate these alkynes, we can get really useful strong carbon nucleophiles called acetylates.